I'm assuming most of you have watched the video on stochastic gradient, and what we're going to start with is a sort of recap, but we're not going to do the full treatment of it. So, what is stochastic gradient descent, or I'll just call it sometimes stochastic gradient? It is a variant of gradient descent in which a subset of the data is used at each iteration. And the subset has a name, and that name is sometimes called a batch and sometimes called a mini batch. As far as I know, those are interchangeable terms. And the two algorithms have different theoretical properties which are beyond the scope of what we're doing here. We're more interested in the practical properties. And the punchline is that stochastic gradient is very useful when we have very big data sets. So in the lab, you're asked to load a data set with 1 million something tweets and then compare it to something else, which is not exactly gradient descent, but close enough. Okay, so one thing I wanted to re-talk about, because every year students get confused about this batch size, epoch, iteration. You could probably pronounce it epoch or epic. I don't know. I'm guessing both are acceptable pronunciations. So I want to define them like this. Let's define an iteration as each time you update the weights. So every time you change the weights, W equals W minus alpha, whatever, we're just going to call that an iteration. You might also call it a weight update. And we're going to define an epoch as a full pass through the data set, or roughly speaking, after you have looked at all the data, we're going to say we've done one epoch. Okay, so then how do we compare gradient descent, GD, with stochastic gradient? At gradient descent, each iteration involves computing the gradient, which in this context we'll sometimes call the full gradient to contrast it with what's happening in the stochastic gradient. So at each iteration we'll compute the full gradient, which, if you recall, is going to have a sum over training examples. And that's not just for linear regression, it's for pretty much any problem. The loss, whatever loss you're using, whatever model you're using, the loss is pretty much almost always going to involve a sum over all the training examples, and therefore the gradient of the loss is also going to involve a sum over training examples. So therefore, with regular gradient descent, since each iteration involves computing the gradient, and the gradient involves a sum over all training examples, each iteration involves looking at all the training examples. So we could say that for gradient descent, iterations and epochs are the same thing. But with stochastic gradient, it's different because each iteration involves a subset of the data. And what subset exactly? Well, it's the batch size over n. Because the batch size is how many you're looking at, n is how many there are in total, and so that fraction is the fraction of the total that you've just looked at. So for example, if you have 1,000 training examples and batch size is 10, then you're looking at 1% of the data every time because you're looking at 10 out of 1,000 examples every time. And so you'd need to do 100 of these 1% looking at the data operations to get to the equivalent of looking at everything. And so that's what we would say. In this example, there's 100 iterations per epoch. So we can turn this into a general formula. The number of iterations per epoch is n divided by the batch size. And if you ever get confused, you can just come back to this and solve for the thing that you're looking for. So in our example here, n was 1,000, batch size was 10, so we had 100 iterations per epoch. Okay, so why are we tormenting you with all this terminology? Here's the thing. We need to have conversations where the things we talk about are meaningful to humans. So if I say to you, I did 10 iterations of gradient descent, you'll kind of know what I'm talking about. But if I say I did 10 iterations of stochastic gradient, that doesn't actually really tell you anything about what I just did. Because is 10 iterations a lot? Is 10 iterations a little? It kind of depends. These could be really, really tiny iterations where the batch size is just 1 out of a million training examples. So if I looked at 1 out of a million training examples 10 times, I haven't really done anything. I've hardly looked at any of the data. But if my batch size is really big, then 10 iterations could be a lot. So it's just not useful when humans are communicating with each other to talk about how many iterations of SGD you've done, and that's why we tend to talk about how many epochs we've done, because that makes sense. If I say I've done 10 epochs, that means I've done 10 full passes through the data set, or that equivalent amount of work, regardless of what the batch size is. Questions or comments? Alistair.
So the batches are, I guess, without replacement?
I'll talk about that in a minute.
Yeah.
Yeah. Other questions? Yeah, Jerome.
Would it be fair to say you looked at half an epoch? Because then, like, you not necessarily, or is it you want to?
Sure. I mean, you could say half an epoch. I haven't really seen much of that, but I guess. Sure. Yeah. It tends to be an integer. Okay. Can people see in the back? Or raise your hand if you want me to zoom in a bit. Okay. So termination. So with gradient descent, we were looking at, the whole point of gradient descent was to minimize stuff. How do we know we've reached a minimum? Well, the gradient is 0 there, but the gradient's not going to be exactly numerically 0, both because we're just kind of approaching it gradually, but also you now know about floating point errors. And so we can't really expect the gradient to be literally 0, 0, 0, 0, 0, so we just check that it's very small. And that's what you have done so far. So we check the magnitude of the gradient. Is it less than some little threshold epsilon? And that was our termination condition. With stochastic gradient, you usually have different termination conditions. So first of all, it is slow to check the full gradient. So you don't want to check the magnitude of the full gradient that often, because that involves, again, going through the whole data set, which is the thing you were trying to avoid by doing stochastic gradient. And also, I mean, this is a bit vague, but if you're using stochastic gradient, it probably means you have a big data set. If you have a big data set, things are slow. You just may not have enough time to wait for full convergence or really high accuracy convergence. And you might, it is more typical at that point for people to just start getting desperate and say, look, I can only wait for like 3 hours for this thing to train, so I'm just going to tell it to do 5 epochs, and whatever comes out after that, that's going to have to be good enough for me. So it's pretty common for stochastic gradient for the user to specify the number of epochs, whereas for gradient descent, it would be maybe more common to specify the tolerance or the accuracy that you're looking for. But those are just human factors, really. Learning rate. So according to the theory of stochastic gradient, you're supposed to decrease alpha over time. So we talked about alpha before. That's this controls the size of the step. In reality, people don't necessarily always do that, and things may end up just being fine. We're not going to concern ourselves too much with that here, because typically we're going to be using some software package like TensorFlow that is going to take care of that type of thing for us. And furthermore, we'll end up using some kind of fancier variants of stochastic gradient that adaptively choose the step size and all these kinds of things. So I just wanted to put that out there, but we're not going to focus on it too much. And there's like endless reading and various methods, and it's an active area of research. So the methods people use were often invented in the last few years, as opposed to like, calculus or whatever that were using the same old stuff. Okay, questions about these two sections? Yes, for Khan.
So is there any relation between the number of epochs you normally do when the data set is large to get a good convergence?
There's not exactly a rule of, you can't really know how many epochs you're going to need. You tend to see numbers like 5. You tend not to see numbers like thousands, just because that would probably take too long for a lot of problems people are actually working on. Because, well, if you have a big data set, an epoch means going through that whole big data set, so it could take a long time. So, yeah, you can't really know what a good value is. You could treat that as a hyperparameter in your hyperparameter optimization, but that's a bit tricky because it may just want to do more and more, but you might not have time for it to wait. So that's a little complicated, and we'll see a bit more of that next week. Any other questions? Yes, Shivam.
You're making an assumption that your loss function always converges. Is there a case where a loss function cannot be converged, or like it doesn't have a minimum?
Yeah, is there a case where the loss function doesn't have a minimum? Typically, we'll be dealing with cases where it has a minimum. The bigger problem is if it has too many minima, and we'll talk about that next week as well. There's also cases where the loss function is not smooth or differentiable, and we're not going to say too much about that either. I briefly mentioned it last week, but in all of those weird cases, stochastic gradient seems to work surprisingly well. It seems to kind of magically overcome a lot of problems that traditional methods struggle with, and so that's one of the reasons why it's so popular. But people are still now just understanding why it does all of these great things.
But there are ways to identify that there is no convergence happening. Like, are there ways to identify using the data that I've seen?
Yes. So the question is, are there diagnostics to know am I converging? So the simplest diagnostic, which I'll show you in a few minutes, is you can just plot the loss over time and say, is it going down? And if it's not going down, is it stuck or is it done? It's very hard to know these things, and these issues are going to plague us next couple of weeks, and they're going to plague all of you whenever you're using things like neural networks. So these are not completely solved problems, but they are real problems. What's your name?
Luke.
Luke.
You think like one epoch is like all the same?
One epoch is like you've looked at all the data once.
So like 2 epochs then all data twice?
Correct.
It should be like even slower than regular gradient descent.
Why would it be slower than regular gradient?
Descent only looks through one time, is it?
No, regular gradient descent looks through the data set every iteration, because you start somewhere, compute the gradient, then you move somewhere, you have to compute the gradient at that new place, and that again requires looping over the whole data set.
Yeah, I see.
Aman.
Yeah. So in this algorithm, is there a better way to initialize the initial weights, or is it always random?
There are rules of thumb and tricks for initializing the weights. I'm assuming in one course, 571 or 573, you talked about scaling your features. Yes? Okay. So that's a good idea. I support that as a general practice, and then that makes the choosing of the initialization a little better, but there's still some tricks, like based on the number of features and stuff. As long as you initialize them randomly and not as all zeros, you'll probably be okay. But again, these packages like TensorFlow, they're going to have some default initialization, which will hopefully not be that bad. I don't think it would likely be a good use of your time to try to think of some better initialization, except in the case that we're not going to talk about too much, where you've kind of done some training already and then want to use what you have to initialize something similar. Oh no, we'll talk a bit about that. So in lab 4, we'll do a bit of that. All right, let's move on. So here you go, Alistair, with or without replacement. So the first thing I want to say is I'm not too worried about this, and I don't want you to worry too much about this, but there's actually 3 cases. So the first case is the sort of cross-validation type thing. Cross-validation, you divide into 5 folds. You do fold 1, 2, 3, 4, 5. So if you have batch size 10 and n equals 1,000, that means you have 100 batches. You could think of dividing your data set into, now they're just called batches instead of folds, but it's really the same thing. You could think of shuffling the data set and then saying, here's the first 1%, second 1%, third 1%, and then you'll just read out those batches one at a time. And that's like the completely without replacement version, in the sense that when you're done one epoch, you've literally looked at each training example exactly once. Then there's the middle version where you say, well, I'm just going to grab a random batch of 10 things every time, but I'm not going to be that careful about the shuffling and all that kind of stuff. So I may, in my first batch, have example number 5 in it, and in my second batch, have example number 5 in it again. But at least when I sample those 10 things out of the 1,000, I'll do that without replacement. So it's so confusing because there's actually 2 levels of with or without replacement going on. And then the third is, I'll just randomly sample 10 things every time, but even that sampling is with replacement. So even in in one batch of 10 things, I might have example 5 twice. My understanding is it doesn't really matter which of those things you do. I believe the ones with the most replacement are the ones that the theory is based on, because the theory is about independent IID things and drawn from the data set. But yeah, my understanding is it's not mission critical which of these things you end up picking. And then I've just made a little note for your lab. You should pick one of the first 2 approaches, because the third one is going to break a little part of the lab. I'm going to zoom in even though no one raised their hand. This feels a bit small. Okay. Questions about this? I don't think this is too important, but hey, could be wrong. Okay. So advantages. Why are we doing this to ourselves in the first place? So it's really about big data. And I would turn this question on its head and say, why would you ever do gradient descent? That seems like a ridiculous idea, to spend all that time looping over all those millions of training examples just to perfectly pick your direction for one little step and then do all that work again, right? Why not just spend a little less effort on each step? You don't have to get it perfect, and then do a lot more steps. So from that point of view, I think this actually seems like a very reasonable thing to do. One thing I want to say is that in your lab, I have you comparing scikit-learn's SGD classifier, which is doing logistic regression when you set the loss appropriately, to scikit-learn's logistic regression. Scikit-learn's logistic regression by default is not actually doing gradient descent. It's doing something fancier than gradient descent, but the point is it's still the thing the logistic regression is doing by default has to look through the whole data set at least once per iteration. Maybe it's probably doing even more work per iteration than gradient descent and getting even better iterations. But I just wanted to point out, you're not exactly comparing with gradient descent in the lab, but you're comparing with something that uses all the data, and that's really the main point I'm trying to make. Questions? Hey, we're right on schedule. So, next thing. So here's some plots that I want to show you. Again, I know the order of the lectures was a bit weird here because this is really a direct continuation of last Wednesday's lecture, and I just had this floating point thing in the middle. It's just most of this week's lab was on floating point, and so I wanted to have that lecture first so you could hear that and do most of the lab, even though from the story point of view, it might have made sense to switch these two lectures. But anyways, some of this is about stochastic gradient, but some of this is still about gradient descent to help you solidify your understanding about that, and is sort of a continuation of the class from a week ago, which I guess was the snow day class. Okay, so I'm going to do my usual made up data set that is a 1D linear regression with some outliers. I think I've shown you this data set a few times by now, either in person or in the videos, or both. The outlier part is not actually very important to what I'm about to show you. I could have done it without the outliers, but what's important is just that, again, I only have two parameters, the slope and intercept, so I can make these nice visualizations of the parameter space. So that's why I'm doing this. Okay. So I've showed you these types of plots before when we talked about gradient descent. So this is the parameter space. These the shading and the contours show the loss. So this star is the minimum of loss, and as you move away, the loss gets bigger. And so wherever you start from, you're trying to get to that star. We've talked about that a bunch. By the way, yeah, I didn't want the notebook to be filled with plotting code, so I just put my plot functions in a .py file that's in the same directory, in case you're looking for it, and they're imported at the top. Okay, so here's what we're going to do now. What we're going to do now, I just have some code that does gradient descent. It's not like a general gradient descent code. It's just like a hard-coded for this problem with two parameters thing. W being the slope and beta being the intercept in this case. And what I'm going to do is I'm going to plot you for each iteration the data space and the parameter space. So again, I believe you've also seen similar plots to this probably in the video. And so here I'm calling them epoch, but this is just regular gradient descent right now, so that's the same thing as iterations. But what I'm doing that I believe I didn't do before is I'm actually showing the trajectory. So I'm showing the path as we move along in parameter space. So this was where we started. Then after one gradient step, we moved here. After another gradient step, we moved here. And we're kind of angling in towards the star. But what you notice, and this is one way of talking about why gradient descent is such a bad method, is that at this point here, I only need to move in this direction that's kind of along this shallow part of the contour. So I've already, the valley is kind of oval shaped here. So I've quickly descended down the steep part of the valley, and now I just need to go this way, and it's a very, very shallow slope in this direction. And so the gradient is actually very small already. And as a result, it's causing me to take very small steps. And so it takes many, many, many iterations to actually get there. And you can see that I think I printed out 15 iterations. It's painfully slow to watch the progress. And you might say, okay, just make the learning rate bigger, but you can play around with this. If you make the learning rate just a bit bigger, it immediately blows up. I guess I can do it. So if I make the learning rate, say 1 instead of 0.1, yeah, that doesn't look good at all. This is this thing called where you say that the training diverged. It's that the step is too big. Remember, the derivative, the gradient, is just a local property. So it says if you follow this direction, I promise the loss will go down. Actually, I promise this is the best direction to go in. But that guarantee is only for an infinitely small step. And if your step is too big, you may actually get to a place with a higher loss than the previous thing. And so what's actually happening here, this is what it's called when people say the training diverged, and you start to see stuff like inf and nan and all those things coming out of it. It's because your step was too big. So if you ever, it'll be a lot more competitive against those other methods. So yeah. Maybe. Okay, so now I'm just going to do the same visualization that we just did, but with stochastic gradient. And I want to set alpha back to 0.1 so we can compare with the original thing. Okay, let's just let the code run. So what this is plotting is every epoch. And what we can see is, at least in this made-up example, and it's not like I spent hours and hours trying to find this this perfect example. In a reasonable example, you can see that stochastic gradient in 3 or 4 iterations is getting closer than gradient descent is getting in a bunch of iterations. Again, this is a small data set, so this is not actually when you would want to use stochastic gradient. You could just use one of those other methods and be better than all of these. But the point of this is to build your intuition about what stochastic gradient is doing. And the reason why this step looks so good is because it's actually doing 40 iterations per each epoch. So I'm showing you each epoch, and it looks like, oh, it's just going really well, but I'm not actually plotting at every iteration now. Those good-looking steps are actually the result of 40 steps, which I'll show you in a second, which may be not so great individually, but as you do a bunch of steps, you actually get something pretty good at the end. So that's that. Ooh, too many of these. Okay. And in this case, you have the losses, and for this particular case, stochastic gradient seems to minimize the loss faster. But again, we have to be a little careful here because if we wanted super high accuracy and we ran it for a long, long time, those lines may cross eventually, and we may get regular gradient descent getting higher and higher and higher accuracy, whereas stochastic gradient at some point is just sort of bouncing around. So often in machine learning, we don't care that much about getting super high accuracy when we're solving optimization problems, but we'll also talk more about that next week. Yes, Derek?
Do you ever switch methods halfway through?
Yeah, that question usually comes up. Would you ever switch methods halfway through? Like when those lines cross, why don't you switch from stochastic gradient? So I don't really see people doing that. I don't even see people gradually increasing the batch size, which is like a softer version of what you just said, because you're kind of slowly approaching. I think stochastic gradient with a reasonable batch size just tends to work pretty well. Maybe it's just you never actually get to that point where they cross. You never want to get to that point where you're spending so much time on one iteration, because we don't need those types of accuracies. But it's definitely not something I've seen people do. Yes, Furkan.
Is there any, like say, normal rule regarding the batch size compared to your data?
Is there any
Rule of thumb.
rule of thumb about the batch size? Yeah, so how do you pick the batch size? I would say it's another hyperparameter. You could throw it into your hyperparameter optimization. Sometimes people choose the batch size based on hardware considerations, which we could talk a bit about later, but it may be the hardware you're using can do like 1,000 things in parallel, and so you pick a batch size of 1,000 to maximally make use of your hardware. But often it's just a hyperparameter, and people don't really use their human intuition that much to choose it. Okay, so here's the other plot I wanted to show you per iteration. Let that load. Okay, so these are individual iterations now. Ignore the label. They're not epochs, they're iterations. So what you can see, for example, is these two steps are not really steps in the right direction. This is not really accomplishing that much. And this step here is actually going completely in the wrong direction. And here my batch size is 1. So I have randomly picked a training example, and it's picked a training example that actually is misleading us. It's sending us in the wrong direction. And then it's going back, and then it's going over here, and then it's going over there, and it's going over there. And then by the time you go through the whole data set, you're actually getting a good overall step. So at each iteration, you might be doing something potentially crazy, but the end of the epoch, I mean, I'm not guaranteeing the end of the epoch could still be crazy, but typically it's pretty good. And that's kind of the whole point of this method. Questions? Sam?
So in this implementation of stochastic gradient descent, where exactly does the randomness come in for the code that you plotted above?
Yes, I should fix that. So this implementation is doing what I called like approach number 1 first. So it's just going through the data points in order. But I should have shuffled them before I did that, and I didn't. So I will fix that, and that's where the randomness comes in. Okay, let's take our break. So it's 11:06. Let's resume at 11:11. There's a good point made during the break about the definition of an epoch, which is that I said an epoch is like you've looked at all the training data, but then I mentioned those with replacement methods, and so then maybe you haven't actually looked at all the training data, but we don't really worry about that. So what I should say maybe more precisely is an epoch means you've looked at n training examples, and maybe if you're using those with replacement methods, those n training examples aren't actually the data set because some of them are repeated and some of them are missing, but we don't worry about that in the definition of an epoch. So if the batch size is 10 and the number of examples is 1,000 and you've done 100 iterations, you just call that an epoch regardless of whether you're doing the with replacement or the without replacement. Okay, so back to work here. The next set of demos I have for you is just to explore the role of the learning rate. I just want to give you an intuition for what that learning rate does. It's often varied in a bunch of different ways. Maybe it's picked adaptively using some fancy algorithm. Maybe it's decrease over time. Maybe it's some combination of the two. Maybe it's some way that you don't understand. But you may well find yourself in situations where you need to pick some learning rate hyperparameter, or maybe some initial learning rate hyperparameter that will get changed over time. So it's good to have some intuition about what the learning rate does when you're dealing with these kinds of things. So I just made up some random data, in this case in 10 dimensions. And this is linear regression again. And I just made some plots showing, so first the loss versus iterations, we just saw that. So now, this is now regular gradient descent. So we get this nice smooth decrease in the loss per number of iterations. And then what I'm also doing in these plots is I'm showing you that for different values of the learning rate. So this is just some other problem. It's not exactly the problem I was showing you before, but it's some made-up linear regression problem. And what you can see here is that in this problem that I'm showing you, if I increase the learning rate from 0.5 to 1 to 2 to 4 to 8, things seem to be getting better and better. So as I make bigger steps, I just get where I'm going faster. Because if the loss just goes down really, really fast, that's like the best case scenario. That's what you'd like to do, is decrease the loss as quickly as possible. And so here I'm plotting the number of iterations to reach some predefined accuracy that's like my target accuracy versus alpha, and it's showing that, yeah, as I make the learning rate bigger, things get better. It takes fewer iterations to get to where I'm going. But now, and I've already kind of primed you to know what's going to happen, but I want to look at the plots anyways, is I increase alpha further, and when I make it too big, then I get this thing over here, which is the loss actually going up versus iterations, and then it's just not even plotting anymore. It's probably reached in for NaN or one of those things that's not even plotting. So that's why we have to be careful with these things. We kind of want to get away with bigger steps, but if we make them too big, then the whole thing's just going to blow up. And so here is the bigger version of the plot we saw before. That as I make alpha bigger, it's taking fewer and fewer iterations to reach convergence, except that suddenly the whole thing just blows up and I never get to convergence. Questions about this? Sam?
I was kind of surprised with the large numbers because we were before playing around with, when we changed it from 0.1 to 3, then we saw it blew up.
Yeah, so good point. So Sam's saying I'm surprised about the large numbers. So this is a different problem. I made up different data, different numbers of dimensions. But that brings up a good point, which is that it's hard to have a rule of thumb saying alpha equals 1 is big and alpha equals 0.1 is small. It helps if you scale the data in the sense that the scaling of your data is actually going to result in a scaling of alpha, basically, or what a good alpha would be. And so that's one of many reasons why people do the normalization or the standardization or whatever that you talked about in the other course. It does seem kind of weird, why should the scale of my data affect the learning rate? But basically the learning rate has units in it, and so if you change the units of your data set, it changes the alpha, which is just one of many hassles that we have to deal with here. And so yeah, just for a different problem, we can't really carry over that intuition. But if everyone's kind of scaling things the same way, I mean, I can say just it's a very vague thing, but I wouldn't normally see a learning rate of 1,000. They do seem to be kind of small numbers, and I guess when people are scaling things reasonably, that sort of tends to happen. But it might change from problem to problem. Okay. Yeah, so this is saying that in this particular problem that I'm showing you, when alpha is 32, that's when the whole thing blew up. But before it blew up at alpha equals 16, the convergence was slower. And that's that sort of back and forth thing that I showed you earlier today. So as you make your steps bigger, as long as it's okay to make your steps bigger, that's good because you get where you're going faster. But then right before it blows up, you're in this intermediate zone where convergence is again slower, but it hasn't blown up yet. And that's probably because you're hopping back and forth, and that actually means you need a lot of steps to get where you're going. Whereas if you've taken smaller steps, you might get there more directly. So it's not even like a monotonic relationship. It's like things, if you make the learning rate bigger, things get better, and then they might get worse, and then everything just blows up. So it's a pretty finicky thing to have to deal with, and a lot of the research and advances in the last 5-10 years have been people coming up with better methods to pick the learning rate adaptively in a reasonable way so that you're not spending hours or days trying to tune that particular hyperparameter. Because some hyperparameters might not matter that much. I don't know, if you're dealing with a logistic regression regularization or something in a decision tree or whatever, if you change that hyperparameter, if you double it, you're not going to just fry everything. Maybe things will get a little better or a little worse, but from what you can see here, the learning rate is a super finicky hyperparameter because if you double it, everything might just be toast, and if you have it, things might just be really slow. And so it's an important part of the research field to figure this thing out and try to adaptively set the learning rate well. But yeah, it's a very tough problem. It's a very tough problem because all this optimization is happening in thousands of dimensions, not the 2 dimensions that we've been looking at here. And it's hard for us to conceptualize, but trying to find something in 10,000 dimensions is not an easy task. So it's tough. Okay, any questions about this? Okay, so let's go on to some true-false questions. So you know the drill by now. I have 2 groups of 4 questions for you. Here's the first group. I'll give you a minute to read over, and then we'll do the individual vote. Okay, let's do the individual vote. So raise your hand for true, don't raise your hand for false. Number 1, for stochastic gradient to work, we need to increase the step size as the optimization proceeds. Number 2, stochastic gradient can be used for training many models, including linear regression and random forests. Number 3, an iteration of stochastic gradient might cause the loss to go up, even for a very small learning rate. Number 4, it is reasonable to check whether the loss went up or down after each iteration of stochastic gradient. Okay, I'll give you a few minutes to discuss these.
I don't think.
Yeah, it gets more random as you parameters aren't used in the that's all. Like making models, right? Like it has a numerical set of it doesn't make sense. Like, as long as it is a trend, smaller loss or something. How are you doing?
I think we're I don't think
Well, I have no idea because when you
Oh, so this should be. I have it.
But yes,
Oh, sorry, I'm not.
Like, you guys see it's just like at scale. Something like I don't know why these are
Okay, let's do the second vote. So, number one, for stochastic gradient to work, we need to increase the step size as optimization proceeds. Okay, my answer here is false as well. Theoretically, we should actually be decreasing alpha as optimization proceeds, although you may be able to get away with leaving it constant, even though that sort of violates the theory. Number two, stochastic gradient can be used for training many models, including linear regression and random forests. Okay, my answer here is false. So it can be used for training many models, including linear regression. I agree. However, training random forests or training decision trees, for that matter, that's a discrete optimization problem. And for each split, we have to decide which feature am I picking, and then we have to pick which split am I going to do. So we talked a bit in the algorithms course about the difference between discrete optimization and continuous optimization. So finding shortest path in a graph would be discrete optimization, or that seam carving we did. So these, as soon as you say the word gradient, you're kind of talking about calculus and continuous math. And so we're applying that to continuous optimization. So there's 2 points here I want to make. First of all, a lot of people think stochastic gradient is just for neural networks. But I want to make the point that no, it can actually be used for many things, like logistic regression in your lab, but not everything, just a lot of things. Reiko.
Could you use it for SVCs?
Could use it for support vector machines. Yes. Yes, you should be able to.
Whether or not it's a classification or regression task.
Aha, right. This came up on Slack as well. This issue between discrete parameters versus discrete features or discrete outputs. So, right, it doesn't matter if the target values are discrete or continuous, meaning it doesn't matter if you're doing classification or regression. It doesn't really matter even necessarily if the features are discrete or continuous. What matters about the parameters, because the optimization is in the parameter space. The parameters are things you're trying to jiggle around to minimize your loss, and so if the parameters in logistic regression, SVM, linear regression are all neural networks, as we'll see, those are continuous valued parameters, whereas in the trees, the parameters, like should I use this feature or this feature or this feature, are discrete parameters. Shivan.
In linear regression, simply doing the differential of a loss function would make better sense than doing a gradient descent algorithm, because you can differentiate and get to know what's the point.
So in linear regression, it's true that you can do the normal equations and get the parameters, the optimal parameters in closed form without doing this type of iterative optimization thing. However, if your data set is really, really big, then you may not be able to do the normal equations. It may be too slow. And so what you would be doing with stochastic gradient is you'd be trading off accuracy for speed. So you may not run that many iterations because your data set's so big, but maybe you don't care about getting exactly the right weights. You just want something good enough. And for sufficiently big data sets, you may even want to do this for linear regression. Good question. Number 3. An iteration of stochastic gradient might cause the loss to go up even for a very small learning rate. Okay, my answer here is true. With regular gradient descent, there is this kind of promise that if everything is nice and the assumptions are all there, that if alpha is really, really small enough, the loss is guaranteed to go down, because that's kind of the definition of the gradient. But for stochastic gradient, that might not be true, because the loss is with respect to all the training examples, but you've just picked one or a few training examples and took the gradient just based on those. And so it may do something silly if you picked some not very representative training examples. So, true. Questions about this? Yes?
If it would have, the statement would have had an epoch, then it would have been false. Because
Aha, if it said an epoch of stochastic gradient. So, even then, yikes. I'm not sure even then. It would probably go down after an entire epoch, but I'm not sure I can make that a guarantee. I'll have to think about that. Number 4. It is reasonable to check whether the loss went up or down after each iteration of stochastic gradient. Okay, so my answer here is false, and I think this is an important one because it kind of illustrates one of the challenges here with stochastic gradient is not only could the loss go up, but you don't know if it went up or down. And the reason is calculating the loss is an O of n operation. It's the sum over all training examples. Did I talk about this in the video?
Yeah.
Okay, never mind. Skip it. You know what I'm talking about. It takes too long. Okay, next one. Here we go. I'll give you a few minutes to read these. Okay, preliminary vote. Increasing the batch size results in slower but better iterations. Number 2, if you double the number of epochs and double the batch size, then nothing has changed. Number 3, one epoch of stochastic gradient takes about the same amount of time as one iteration of gradient descent. Number 4, stochastic gradient with a mini batch size of n is the same thing as gradient descent. Okay, take a few minutes to discuss.
As many batch size, as many batches.
Yeah, one batch, one green coffee.
Okay, do we go with the other ones?
So you know the answers, Carlos? You guess so? Have you studied this before?
I don't know.
Oh, you're learning some new stuff in some courses? All right. Matt looks ready. So let's do the second vote. Number one. Increasing the batch size results in slower but better iterations. Okay, my answer here is true. Increasing the batch size means we're going to look at more data, which should be better than looking at less data. It could happen, again, there's randomness here in stochastic gradient descent. That's why I'm hesitant to say these absolutes. You might get a worse step even if you looked at more data just by bad luck. But in general, I would expect that having a bigger batch size will result in slower but better iterations. And so to reach a certain accuracy, if each iteration is better, hopefully you need fewer iterations. But now it's slower, but you don't need as many of them. And the question is, was it a good deal or not? And it's pretty hard to say in general, which is why you might optimize the batch size as a hyperparameter. Number two, if you double number of epochs and double the batch size, then nothing has changed. Okay, so my answer here is false. It is true that the number of iterations has not changed because, well, it's a bit hard to articulate. If we go back to our example with n equals 1,000 and a batch size of 10, and we're doing one epoch, then that would be 100 iterations. If our batch size was 20 and we were doing 2 epochs, it would still be 100 iterations. But something has changed because we're actually doing more optimization here. So for example, the whole thing's going to take longer. And so maybe not exactly twice as long. That's the thing. When you change the batch size, the time to do one epoch may change depending on... That would be a good true or false question. But yeah, so something has changed in terms of the amount of optimization you have, but also something, namely the number of iterations, has not changed. Yeah, so the question I was alluding to is, if you change the batch size, does the amount of time it takes to do one epoch change? And that's a complicated question, because in terms of like big O, it doesn't, because either way you end up just looking at the whole data set, because that's the definition of an epoch. But due to implementation considerations, hardware considerations, vectorization, parallelization, the kinds of stuff we talked about at the end, it may actually change the speed. Any questions about number 1 or 2? Yeah, so Manuel.
Again, why does it change optimization, please?
Can I explain again?
Why it changes optimization?
Why it changes optimization. So the definition of an epoch is, it's a measure of how much optimization you did, or how many times n points you look at. So one epoch means that you looked through n data points. 2 epochs means you looked through 2n data points. So by changing the number of epochs, I'm always changing something because I'm looking through more data points in total. But I kind of tried to throw you off by saying also double the batch size, and that means that something hasn't changed, which is again the number of iterations. Number 3. One epoch of stochastic gradient takes about the same amount of time as one iteration of gradient descent. Okay, my answer here is true. Again, it may not be exactly the same amount of time, but one iteration of gradient descent means you've gone through the whole data set. The definition of one epoch of stochastic gradient is that you've gone through one data set. So they should take, roughly speaking, the same amount of time. Again, there's implementation considerations of vectorization and all that kind of stuff, but about the same amount of time. Yes, Jerome.
Does it depend on how fast you can evaluate the gradient? Because SGD is evaluating the gradient at each iteration.
Well, that's the thing. Right. The question, Jerome's question was, does it depend on how fast you can evaluate the gradient? Well, it does, but if I evaluate the gradient based on the whole data set, that's probably going to take twice as long as evaluating the gradient based on half the data set. Because inside that evaluating the gradient, even if you look at the code I gave you in Lab 1 for logistic regression, you're going to see that np.sum. There's going to be typically some sort of aggregation over all the examples, and so if you're not looking at as many examples, it should be that much faster. Sam.
So is it also fair to say that, like, for example, 100 epochs of SGD takes about the same amount of time as 100 iterations?
Yes, sure. 100 epochs of SGD takes about the same amount of time as 100 iterations of GD, sure. Andres.
What if you're using approaches with replacement?
Louder, please.
What if you use approaches with replacement?
Yeah, what if you use approaches with replacement? So that shouldn't affect the speed. And that goes back to that clarification I made just after the break, is that maybe my definition of epoch, I should have said, it means you've gone through n examples rather than you've gone through exactly the training set. Yes, Carrie.
I'm a bit confused now about SGD. So is the goal to run through all of your data sets, or is that like going to happen anyway? Because if you reduce your batch size, will you then perform enough iterations to get a full epoch, or can you do like half an epoch?
So generally, you probably wouldn't do less than one epoch, because if you did less than one, that means you haven't even looked at all your training data, and then you might as well not have that training data. Going back to what you're saying, the goal of stochastic gradient, there's always going to be this trade-off between speed and accuracy. If you do more iterations, it'll take longer, but you'll get more accuracy. So your reason for doing it could be that you just don't have enough time and you want it to be faster, or you're willing to spend that same amount of time, but you want to get better accuracy. But either way, it tends to have a better accuracy gain per minute or per hour or whatever. And the reason for that is that instead of spending a very long time deciding what step to take, it spends very little time, so it takes a bunch of steps, And then after that same hour, you've probably gotten farther with a bunch of bad steps than one good step.
And if you create your batches with replacement, you might, is it true that you might not actually hit all the training?
Yes, if you do things with replacement, then after one epoch, you may not have seen every training example, and I'm just sort of sweeping that under the rug and saying, let's not worry about it.
Thank you.
And last one, number 4, stochastic gradient with a mini batch size of n is the same thing as gradient descent. Okay, yeah, sure. I mean, other than that replacement stuff that we talked about, if you're doing it fully without replacement, then it's going to be the same thing as gradient descent. Don't leave yet. I just want to make a couple of quick clarifications that I wrote down in lab on Monday and Tuesday about the floating point stuff. I think there were some recurring points of confusion I just want to mention in the last few minutes. So, number 1, I realized I never actually mentioned those special values inf, nan, minus inf, but NumPy has them. Most numerical programming languages have them. R will have them. So basically, they just reserved some numbers to be inf or nan or whatever. And basically, inf is if the number was too big that it was going to overflow, NumPy just sets it to inf instead of throwing an error, whereas base Python throws an error. And that's often pretty useful because then it'll allow you to see that inf, and you as the programmer decide how to handle it. If it's inf, do this. Whereas just throwing an error, then it's kind of more of a hassle. And in particular, if you're later going to do something like 1 over x, and x has overflowed to inf, then 1 over inf is going to return 0. And that's actually good, because 1 over some ridiculously huge thing is very close to 0. And so then your code can kind of proceed, and it may not have been that big of a deal. So forgot to mention those things. A general thing I want to talk about too, so in class last time I did that log 1 plus e to the x thing, and then in the lab you have that Gaussian PDF thing. There's a general theme with all of this, which is that usually the end result you're trying to get is a reasonable number, but it's an intermediate quantity that you get on the way to computing what you're computing that causes the problem, like the overflow. So log 1 plus e to the 1,000. 1,000 is a fine number.